Good day to my wonderful SS3 students. I welcome you all to this learning. Today we are going to be treating a topic termed nuclear physics. By the end of this lesson, the students should be able to, number one, distinguish between nuclear fission and fusion. Number two, mention the advantages of fusion over fission. Number three, highlight some peaceful uses of nuclear energy. And four, solve related problems on nuclear reactions. Let's go into the topic proper. What is nuclear reaction? This is a reaction that involves the production of nuclear energy. Generally, in nuclear reaction, it is observed that the mass of the product is usually different from that of the reactant. What do we mean by that? The total mass of the component products is less than the mass of the original element. And this difference in mass, which is also called the mass defect, is a measure of the nuclear energy released. According to the physicist Albert Einstein, we have an equation for that, which is E is equals to delta mc squared, where E there is for the energy released, delta m is the mass defect, while c is our speed of light, which we already know the value for that, and that is 3 times 10 raised to power 8 meters per second. In nuclear energy, the unit of energy is called the electron volt, abbreviated small letter E, capital V. And 1 electron volt is equivalent to 1.6 times 10 raised to power minus 19 joules, which we can also convert to mega electron volts, and 1 mega electron volt will now give us 1.6 times 10 raised to power minus 13 joules. The unit of energy also is expressed in unified atomic mass, AMU, which is denoted by the capital letter U. And 1 unified atomic mass is equals to 931 mega electron volts. From there you can convert to what? Joules. Let's look at what nuclear fission is. You must have done this in chemistry, but we'll take that again. Nuclear fission is the splitting up of the nucleus of a heavy element into 2 approximate equal parts, with the release of huge amount of energy and neutrons. We have a typical equation there, which is the bombardment of uranium atom and neutron. You can see uranium 235 is the atomic mass, and the mass number is 92. It's being bombarded with neutron, and what happens there? An isotope of uranium is formed, which is uranium-236. This uranium-236 is unstable, and because it's unstable, it breaks up into 2 other elements, barium and krypton. Barium is having a mass number of 141, an atomic number of 56, while krypton is having a mass number of 92, while the atomic number is 36. And this also results in the release of neutron also plus energy. Under that, we have that when uranium atom absorbs or captures a fast-moving neutron, the nucleus breaks up into barium and krypton with release of neutrons and energy. Then we have that if this in turn can be captured by other uranium nuclei, the number of atoms that undergo fission would multiply rapidly. What do we mean by that? That neutron that is formed from the splitting of the uranium-236, if it captures another uranium nuclei, there will be multiplication of what? The fission process. And this multiplication action is called chain reaction and may lead to explosion, provided the critical mass of the uranium is not exceeded. What is then chain reaction? And simply, chain reaction is defined as the rapid multiplication of a fission process by fissile neutrons. What are the conditions for chain reaction to occur? Number one, the mass of the fissile material must exceed the critical mass. And number two, in addition to the two nuclei produced during the fission, 1 to 3 neutrons must be produced per parent nucleus. The components in a nuclear reactor used to control chain reaction, because if it is not controlled, there will be steady multiplication of this process. So we have some component in a chain reactor, which is what the instrument for producing this chain reaction, and we have some components to control this multiplication. And we have boron steel, we have heavy water, which is also called deuterium oxide, and we can also use graphite or carbon rod. Finally, we have that fission is also the process used in the present-day nuclear power stations. What then is nuclear fusion? And we have that nuclear fusion is a nuclear process in which two or more light nuclei combine or fuse to form a heavier nucleus with the release of a large amount of energy. We have three equations there. We can see the first one, magnesium bombarded with a helium or combining with a helium atom to form silicon. The second one, we have beryllium with hydrogen there forming carbon. And the third one, we have tritium and deuterium combining to form a helium atom with a release of huge energy and also neutron. The third equation there occurs mainly in the sun. So we have under there that the fusion of tritium and deuterium in the sun produces enormous energy, as shown in the reaction above. That is the third reaction there. The reaction is termed thermonuclear fusion because it requires extremely high temperature. We take a subheading there, advantages of fusion over fission. The first advantage there, please take note, this is an important question in WAEC. Number one there, fusion is more easily achieved with lightest elements such as hydrogen. Number two, the raw materials required for fusion are more cheaply and readily available. And number three, we have that fusion process produces less dangerous, in other words, non-radioactive byproduct. And finally, number four, there is no upper limit to the mass of hydrogen that can be exploded or produced in a nuclear fusion process, so very large energies can be obtained. These are the four advantages that fusion have over fusion. And one side disadvantage is that it requires very high temperature. Take note of that. Just that fusion process requires very high temperature. What are the peaceful uses of nuclear energy? Number one, in medical field for radiotherapy. Number two, in industry for the production of cheap electricity from nuclear reactors and powering spacecrafts, ships, and submarines. Number three, in agriculture as radioactive tracers and preservatives. Four, in the treatment of tumors. And finally, number four, in food irradiation. Now, we are going to take some calculations on nuclear reaction. Very, very important from the things we have done so far. Let's take some calculations. The first calculation we have there is in a nuclear fusion experiment, the loss of mass amounts to 1 times 10 raised to power minus 6 kg. What is the amount of energy obtained from the fusion? And in bracket we have our speed of light to be 3 times 10 raised to power 8 meters per second. Now if you look at that question, the solution to that question, we are using the formula E is equal to delta mc squared. If we substitute that, we have the amount of energy obtained to be equals to difference in mass there is 1 times 10 raised to power minus 6, and we have multiplied by the speed of light 3 times 10 raised to power 8 meters per second, and it is squared. If we do the multiplication with our punch cards, we will be having the final answer to that question is that E, the energy released, is equals to 9 times 10 raised to power 10 joules. We take the second question there. In a thermonuclear reaction, the total mass reaction is 3.02 multiplied by 10 raised to power minus 27 kilograms, and the final mass after reaction is x kilograms. If the energy released in the process is 8.5 multiplied by 10 raised to power minus 12 joules, calculate x kg, where in bracket there our speed of light is 3 times 10 raised to power 8 meters per second. Let's look at the solution to that question. If you look at that question, you will agree with me that what we are looking at for there is our initial mass, because we are looking for our final mass. Initial mass was given there as 3.02 times 10 raised to power minus 27 kg. So what do? We need to find our mass defect first, the difference in mass. When we get that, we can now do the normal thing we are supposed to do to get the final mass. Okay, let's introduce our equation again for the solution to that question, which is E is equal to delta mc squared. If we make delta m the subject formula, we have that delta m is now equal to E all over C. If we do the appropriate in there, we have 8.5 times 10 raised to power minus 12 all over 3 times 10 raised to power 8 all squared. Then that will give us 9.4 times 10 raised to power minus 29 kg. So that's our difference in mass or mass defect. Now, using the formula again, that the mass defect will be given by initial mass minus final mass. Recall that our final mass is x, so we will be having that our final mass, which is E2 now, is equals to delta m minus E1, and that to make our x to be equals to I think there is an error there, because if we look at that, we will see that if we make E2 going over to the other side, E2 should be E2 now becomes E1 minus delta M. So X now should be 3.02 times 10 raised to power minus 27, okay, minus 9.4 times 10 raised to power minus 29. Please take note of that. So the final answer there, which we have 2.93 times 10 raised to power minus 27 kg. So take note of that correction there. So the answer might not be 2.93, but it must be 10 raised to power minus 27 kg. Take note of that, please. Sorry for that. We now take the last calculation there. Calculate the binding energy for sodium 23. That is, the mass number is 23 and the atomic number is 11. Please pay attention very well. This calculation is very, very important in your school exam and WAEC. Okay. Under the question, we were asked to take the atomic mass of sodium to be 22.989771 U. Mass of proton is equals to 1.007825 U. Mass of neutron equals to 1.008665 U, and U is equals to 931 mega electron volts. Okay. Pay attention as we solve. We take the solution to that question. First of all, we need to get our number of neutrons, and how to get neutrons, you multiply, you minus the atomic number from the mass number, and if we do that, we have 23 minus 11, which makes our neutron number to be 12. So now let's get the mass of neutron. Now the mass of neutron now becomes 12 multiplied by 1.008665 U, and that gives us 12.10398 U. Mass of proton will now be 11 multiplied by 1.007825 U, which will now give us 11.086075 U. Now let's get our mass defect. Our mass defect now will now be, if we add the mass of neutrons and mass of protons, we'll be having 12.10398 U plus 11.086075 U minus what? The atomic mass, which is 22.989771 U. Under that, we have that the mass defect becomes 23.190055 U minus 22.989771 U, and the answer to that becomes our binding energy. Remember, we said that our mass defect is the binding energy, or the energy released. So we have that binding energy becomes 0.200284 U. Okay, if we multiply that by the value of U, we have 0.200284 times 931, and that gives us 186.5 mega electron volts. Now converting these mega electron volts to joules, we'll now have that the binding energy finally is 186.5 multiplied by 1.6 times 10 raised to the power minus 13, and that makes our final answer to be equals to 2.98 times 10 raised to the power minus 11 joules. That is our binding energy. Okay. All right. That is where we are going to stop for now, and I will be leaving you with this assignment. Number 1, a material of mass 10 times 10 raised to the power 3 kilograms undergoes a fission process which decreases its mass by 0.02%. Calculate the amount of energy released in the process, and the speed of light there is 3 times 10 raised to the power 8 meters per second. So you should be able to solve that, because you have to get the final mass by doing the mathematics there. If you have the initial mass to be 10 times 10 raised to power minus 3. Then the final mass, now you know how to do this by multiplying by the percentage you have there, 0.02. Okay, number 2, calculate in joules the binding energy for thorium of mass number 234 and atomic number 90. And we have the atomic mass of thorium there, 234.11650 U, mass of proton 1.00738 U, and mass of neutron 1.00867 U, and 1 U is equal to 931 mega electron volts, and 1 electron volt is equal to 1.6 times 10 raised to power minus 19 joules. Okay, thanks for listening. Till we meet in our next class, please remember to stay actively safe. All right, bye.